Welcome everybody. This is going to be a short demonstration and training session on a new AFM that's here at the university called the Bruker Multimode 8. And that is the instrument that we have, you see, sitting in the cabinet here. So the plan for the session today will be to give you a general introduction to this instrument, how it operates, and the way to set it up to get a good image first time out of it, and how to safely operate it so as not to break it or damage it. So what I'll do first is we're going to talk about the main components that make up this AFM system. And AFM here stands for Atomic Force Microscope. So the instrument has multiple features or multiple hardwares that make it up and make it work. So obviously we have something to control the instrument. That's our PC. So you'll see the PC sitting underneath the bench here, and you'll also see the PC monitor, keyboard and mouse, as we would all expect. If we move across to the system, under the bench here we have a fiber light, and that provides an illumination source so that we can see a sample surface, and we'll talk about that in a little bit. If we move further across, this big enclosure that you see here, this is an acoustic enclosure, and the purpose of this enclosure is to try and damp down acoustic noise. So it could be from talking, it could be from people moving around the lab, or other instruments in the lab that emit vibration as acoustic waves or as noise that we hear with our ears. The purpose of this is to try and damp that down so it doesn't affect the measurement that we're making on our instrument. Okay, so inside this enclosure here, we have essentially three parts. So we have this lower part here, which is a vibration isolation platform. And the purpose of this vibration isolation platform is to take out vibrations that may be coming from the ground. So similar to the acoustic enclosure here, which takes out noise propagating through the air, the vibration isolation platform reduces the noise that's coming up through the floor. So it could be actually people physically walking, or it could be the building swaying, or even heavy-duty trucks driving up and down the road. So the purpose of this is to provide a stable platform for the rest of the AFM to work on in order to get the most level of resolution out of this tool. So we'll go through this in a little bit, but before we get to this section here, I just want to point out down underneath the instrument here, we have the AFM controller. So this AFM controller here, you can think of it as like the brains of the instrument. So this instrument here has a number of signals which we send to the instrument in order to get it to do something, and then it detects information, and that information all passes down into this controller here, and then is processed in this controller and passed over to the PC. So this is what we call the Nanoscope 6 Atomic Force Microscope controller. And the signals are passed up from the controller up into the instrument through a ribbon cable, which you see coming up into this side of the instrument here. Okay, so inside this enclosure then, sitting on top of our vibration isolation platform, we have then another base structure, which is this granite base here with a translation stage that you can see. There is a pillar that rises up the back, and we have optical system top down, so we can see a sample surface. And that sample surface is something that we're going to place into a space into here, where you can see I'm pointing with these tweezers. Okay? And so we'll go through that in a few minutes. And this part of the instrument here that we can see, this is the atomic force microscope. So we have a base, a precision scanner, which can move at angstrom levels and even sub-angstrom levels, so smaller than nanometers, really down into the atomic scale. And we have a laser deflection system, which again we will talk about in a little while, a probe holder, and finally our sample. So what we're going to do now is we're going to break this instrument down into its components, and we'll talk about each of them individually. So what we'll do now is we're going to talk a little bit about the setup of the instrument under normal operating conditions. And so the first thing that we want to check when we start is, do we have a source of air coming into this table here? And so that is done through this pressure regulator which is sitting over here. Now this pressure regulator that you've just seen here, this is sitting at around 3.5 bar or around about 50 psi, and that's the pressure that allows this to float. So if I press on this corner, you can see that will compress down. So we're sitting on this nice soft cushion of the air in here. Now, in terms of getting the instrument set up, what we need to do first is we need to power everything up. So what we're going to do is we're going to power on the PC, we're going to power on the nanoscope controller, which is sitting underneath, and also the light source, which you will have seen before, which is down here. So let me just switch that on. Okay, and we're going to start our nanoscope software. So on the desktop of the PC here, we have a number of icons, and one of them will be called the Nanoscope 10.0 in the current generation. So let me double click that. Okay, so we have then software which opens up, and this software, when it opens up here, will ask us first what type of mode that we want to be in. And so that mode we can choose, and we'll talk about that a little bit later. So let's just start in a mode that we can begin to set the instrument up. So I've just chosen one that's called Scan Assist mode. So this is a simple operation mode that the system can use for imaging the surface. So I'm going to turn this light source down a little bit so that we can see the sample surface. Okay, so once this is opened up, what we have here is we have a setup script that runs down the left-hand side. We have parameters that run in this top left side here. We have some feedback of the instrument that we can use to determine are we working well or not. And then we have the scanning and imaging parameters in the center. And over on the right-hand side here, we have our output, the files that we save, the scans that we've done. Okay, so once we have this software opened up, what we will do is we will load a sample into the system over here. We will load a probe, and now the purpose for what we need to do next is to align the laser to the back of the cantilever beam and then align that to the detector, and we will talk about that as well. So if we look at this system here now, what we have is we have the AFM base like we were talking about before, which has, as you remember, a switch on the left-hand side that determines the mode and the information that we see on this front screen. And we have an up and down switch which pushes the entire sample head up and down. We have our scanner sitting on top of that, and then the AFM head sitting on top of the scanner. Inside the AFM head here in this region, we will put our sample and we'll put our AFM probe holder. And then above that, we're going to align this optical system to focus on the sample surface. So we'll do that first so we can see. Now I've already placed a sample in, and we'll go through that shortly. So, all right. So what we see over here, I've undocked this window, which is our video window. That'll allow me to see a little bit easier when I'm operating the instrument. So what I'm going to do is I'm going to bring the sample into focus. So if you have a look at the screen, what you see now is you see that the sample is nicely in focus through this optical camera system. Now, if I move that focus up at some point, I should be able to see the cantilever that I'm looking at. Okay, almost. All right. So if you don't see your sample, if you don't see the cantilever beam, the probe that we've installed over here, we need to then move the system underneath the optical surface in order to see that. So if I focus up here, so I see the edge of my chip here, but I don't see the actual cantilever beam which is making the measurement. So what I need to do now is I need to move the entire system underneath the optics, and we have two knobs. We have one here for moving the system back and forth, and then one on the right hand side here for moving it left and right. So let's go ahead and bring this into the field of view that we can see, and I'm going to put the tip of the cantilever here. I'm going to put that roughly into the center. It doesn't have to be perfectly into the center, but roughly into the center. Okay, so this particular probe that we're using is a triangular based probe. So we see two arms coming in, one from the bottom, one from the top. The shadow that's on the right hand side here is the cantilever chip, and we've discussed that. And this particular type of probe is called a scan assist air. That's the probe that we've installed in this case. So what we're going to do now is we're focused on the tip. We can see that that's within our video view. I'm going to roll the focus down to find my sample surface, okay, like this. And now what we're going to do, that we've found the sample surface, is we're going to bring that AFM probe down. And bringing that AFM probe down, we have the switch that sits on the right-hand side here, which has tip up and tip down. So we want to move this tip down. So I'm going to actuate that probe, that switch, move it to the back. And then I'm going to look and see when I start to see the shadow of that cantilever beam starting to come into focus. Now, I don't want it to be perfectly in focus because that means we crash to the surface. I just want to get it close so that I don't have to wait. Okay, so now that you see that we are here close to the surface, our next step is to align the laser to the back of this cantilever. Okay, so now that you've seen the basic hardware that makes up this atomic force microscope, what is the atomic force microscope? Well, the concept of the atomic force microscope is that we're going to take something which is very, very sharp, like a very fine needle, and we're going to press that into a surface, and we're going to try and feel the interaction between that very sharp needle and the very top layer of the surface. And that interaction that we feel is done by taking a laser, shining it to the back of a flexible cantilever beam, and then reflecting that laser off the back of the cantilever to a detector that can monitor as this cantilever beam is bending. So this is called a position-sensitive detector or a quadrant cell detector. So this scheme that you see here now, we have our PC controlling the controller. We take some of the signal, we turn the laser on, we shine it to the back of our flexible cantilever beam. That reflects up to the quadrant cell detector. And if we have a look at the interaction at the very apex of the tip, interacting with our sample surface, we really are trying to control the interaction of a few atoms around the AFM tip with the atom or molecular structure of the surface. And so we do that in feedback. Okay. So what we need to do now is take that laser and get it to the back of this cantilever beam. Now what we've done here is we've installed a sample which allows us to reflect a little bit of that laser light off so we can easily see. So you remember over on when we talked about the AFM head, you'll remember that we had two knobs which were for adjusting the position of the laser, and we had two knobs that were for adjusting the position of the photodetector. So what I'm going to do now is I'm going to adjust the position of the laser because we need to catch the laser spot to the back of the cantilever beam. So that's the first thing that I'm going to do. And the easiest way to do that is to bring the cantilever close to the surface, and then once it's close to the surface, I can see the position of the laser spot, and I can adjust the two knobs here in order to bring it in. Okay, so if I just park it here for the moment, what you can see on the screen now is our laser spot is sitting here. Okay, and so I need to take this laser spot that's here and I need to bring it over to here. Okay, so what we'll do is adjust this in one axis here to see, and then in this other axis over here bring it across like this. Okay. Now, as I do that, as I start to catch the laser to the back of the cantilever, what I have then is I can start to see down here some signals start to appear. And the signal that I'm interested at this point is called the sum signal. So the sum signal is just the signal off the photodetector, all of that signal summed together to give us some value down here which we can see. So when my cantilever, or when my laser is off the cantilever beam, I don't catch it at all, my sum signal here is 0, or very, very close to 0. If I bring my laser across and it touches to the back of the cantilever, you see that sum signal will go up. Okay? Now for this type of probe, if I continue, that sum signal will drop. Okay? So I'm going to come back and I'm going to maximize the signal in one axis and maximize the signal in this other axis here. And just keep working this until that signal becomes nice and strong. For this type of cantilever, we're expecting somewhere between usually around 4, 5 or 6 here. Usually around 4, 4.5 is normal. This particular probe is around 3.8, 3.9. So what we have now is we have the sample which we focused on. We've brought the tip down in close and we can see a little bit of red scatter from the laser just passing off the edges of this cantilever beam. And we see now down here we have a nice strong sum signal. So what we're going to do now is we need to adjust the photodetector so that the laser beam passes directly to the center of that photodetector. This is where it's going to be the most sensitive for the purposes of the AFM. So over on this side of the probe, of the system, I have two knobs, one at the top which you can see and one directly in line with that at the back. And so these are adjusting the signals which are called here VERT or vertical and HORZ or horizontal. So we're moving the photodetector, our laser is bouncing off the surface, it's coming up to the photodetector here and we're just moving the photodetector up and horizontally to bring these two signals that are here to 0. So it's not like with the sum signal where we try and maximize it. For this purpose, we're taking the vertical signal and horizontal signal and we're making those come to 0 or close to it. Now, it doesn't have to be exactly 0. We don't want to spend tens of minutes trying to make, the absolute number perfectly to 0. But if you can get it less than 0.1 in both axes, that's more than good enough for doing imaging with this system. Okay. So, something like this. So we have now a nice strong sum signal, which is 6.23. We have a vertical signal at negative 0.07 or 9, depending on the time that I'm talking about it, and a horizontal signal at 0.03. So here now we know that the laser is coming down, as we were talking about before. It's hitting the back of the cantilever beam. It's striking the back of that cantilever, shooting off to the detector, and now we're catching that laser beam directly on the detector in its center. So this is the next step in setting up the system. All right, so now what we have the hardware of the instrument set up, ready to go. What we're going to do now is look at starting an AFM scan. So taking the probe, landing it to a surface, and then starting to image. So at the moment, my video window, which is here, I've expanded that out. So I just want to seat that back into the main window. I'm going to right click here, and I'm going to press Dock, Undock, and so that's going to bring the video back here. Now, if for some reason you ever lose the video can be accessed by a button up the top here. And if I just hover over this icon, you see it says video, so I can hide that video altogether if I don't want it. All right, so the first step in actually performing a scan of the surface is we're going to start by looking at this workflow here. And if you look at the workflow, it says setup, check the parameters, engage, scan and ramp, and withdraw. So we're going to follow this process in order to start to image. It's very logical and sequential. So I'm going to start in the setup window. When I move to the setup window here, I see this main screen change. And the main thing that I'm looking for now is I want to choose specifically what is this probe. So I'm going to choose the probe from the database. Okay. Now the database has many different types of probes in it, which Bruker have as part of their standard catalogue. We can also choose some other probe that maybe we want to use. We don't have to use the Bruker ones, although they do work the best, but we don't have to. And we can define that probe that's an unknown probe in this system as well. So what we're going to do is we're going to choose the probe that I've loaded up. And the probe that I've loaded up is called the Scan Assist Air probe. Now for each different mode of operation, each different imaging mode which we started with, it will have some default recommended probes which you see listed here at the top under recommended probes. So these recommended probes will always be at the top of this list. And then other probes that are available to use are in alphabetical order further down. So we're going to choose Scan Assist Air, the probe that we've installed into the system. And I'm going to press here, return and save changes. So what's happening at this point, each probe has its own particular parameters. Those parameters are things like their resonant frequency, the length, the stiffness of the probe, the deflection sensitivity of the probe, and the probe radius, the cone angle, the tip sharpness, things like that. So all of that information is stored in a database in the back end of the software. So when I choose the probe here and I return and save changes, it loads all of that information into the system, so we don't have to do that. So I'm done with this window that's called Probe Setup. I've gone Probe Setup, I've chosen the probe. Second one here, place the crosshair on the probe. That just tells the system where we are if we ever go completely out of focus. And check parameters. Now, for Scan Assist Air mode of operation, we don't need many parameters. The system can do the thinking for us while we're imaging. But if we have a look at the simple parameters that we have scanning parameters. So things such as the size of the scan. In this particular system, our scan size could be from few nanometers up to around about 10 to 15 microns. We have aspect ratio. Do we want a square? Do we want a letterbox coming out? We can use a letterbox to speed up the imaging of the surface if we wanted to just have a small section like a step profile. If you want to do a full area like an image for roughness analysis, you would leave aspect ratio to 1. You have offsets. So if the feature that I want, which could be at very much a nanoscale, isn't in the center of the field of view, and I want to bring that to the center of field of view, then we will have an offset associated with the positioning system. We have a scan angle, which is determined, are we scanning in X? Are we scanning in Y? Scanning in X is 0 degrees. Scanning in Y is 90 degrees. But we can choose any angle that we want in order to rotate the image to give us the exact orientation that we would like for the publications. We have a scan rate in hertz. So this is the line rate. When I scan across once and come back, that's the rate at which I'm scanning that line. Bearing in mind we're building up a square or a letterbox profile. And then I determine the number of lines in the image and the number of data points in each line. And so that is samples per line and number of lines. Now, we also have other parameters such as feedback, the peak force tapping control and other units. Now, I'm going to turn the peak force tapping control frequency to 2 kilohertz for this case, but I'm going to leave this parameter called Scan Assist Auto Control. I'm going to have that turned on. So once we're happy with the parameters that we've set, and maybe I'll set this to be 2 micron to begin with, okay? If we're happy that these parameters are ones that I might want to start with, I can then go ahead and click Engage. Now, when I click Engage, what's going to happen, we're going to start to monitor these signals, in particular the vertical signal here, and we're going to start to monitor that. So as the system moves the probe closer and closer and closer to our sample surface, we want to start to feel that interaction very delicately. Remembering that the apex of the probe that we are working with is a nanometer in size, we don't want to come down very fast and crush that into the surface, because that will cause the probe to break and then we have to start again. What we want is we want to be able to do that in a very well controlled way, in a very well defined way, and so that we can land on the sample surface, we don't break the probe and we don't break the, or don't damage the sample surface. So when I click that Engage button, what's going to happen is we're going to monitor this vertical deflection signal here. The system will start to drive the motor that's in the base and start to bring this whole head, it'll start to bring that whole head down. So we're going to reduce the gap between our tip, which is here. We're going to bring that closer and closer and closer to the surface until we feel some interaction. And that's all done in an automated way. So I'm going to go ahead now and press Engage. Okay. So now what we're doing is we are starting the peak force tapping cycle, and as you can see in the software here, it says we're approaching the surface. So now what we're doing is we are really stepping that motor down. Okay. So we can hear a little beep in the background, and that is the system saying it's engaged with the surface. So one of the first things that we can do to check, are we really actually engaged with the surface? In this mode of operation, we can look to our heartbeat or our peak force trace. So I'm going to right click on it for this purpose and just undock it here, just to make it big enough so that we can see it. So what we see here is we now see some real-time signal of the probe interacting with the sample surface. We are oscillating this probe up and down to bring it towards the sample surface and pull it away. So in time, we start with zero signal. The probe doesn't interact with the sample surface at all. Then we feel some interaction and we get to something called our set point. Once we reach our set point, we're pulling away from the surface and then we feel adhesion. So when we touch the surface, it sticks a little bit to the surface. And as we pull away, we need to break that force of adhesion. And then the cantilever is ringing down at its natural resonant frequency. So this is the first and easiest way to check, are we actually touching the surface? Do we see this heartbeat here? Okay. So let me right click on that and just dock that again. So now that we're engaged with the surface, we can see that we are scanning left and right. In our case, we're just scanning at 1 Hertz, just by default. And as we track across this surface, we've set to 2 microns, we'll start to see some features on the surface. So the size of these particular features are quite small. They'll be in the order of tens of nanometers. For example, this one here is 30 nanometers wide. So really we can see with this AFM down at the nanoscale. Okay. Now we can change the view that we see here by adjusting it from 1-channel view up the top here to a side-by-side 2-channel view to a vertical top-bottom 2-channel view, or if we have different modes with different channels, we can have a 4-up view like this in a square. Okay, so what we have now is we are scanning away on this sample surface here. Now, this is collecting information into what's known as a buffer, just storing it in the background, but it's not saving the data. So what we need to do is we need to save this data somewhere in the system. So in order to do that, our data that we have already scanned is over here on the right-hand side, and our acquisition to save the information is also over on this right-hand side. So what I'm going to do is I'm going to press on this capture icon, select capture directory, this icon here, and I'm going to choose where I want to put this data. Now we have a drive which is called E drive in this system, which is traditionally what we use for storing data. So we're going to go into E drive. We've set up one called training. Now you would normally put that under your username, and then what I would do, or what I would suggest, is have a username, then your project name, and then something specific about this sample that will help you identify it at a later stage. So I'm going to come in here, we're going to click on training. We've already set this up. So that's the directory that I'm going to store data, but it doesn't mean we automatically store that data. What we need to do then is we need to tell the system to capture something. So we have some icons that are here just to the left, which are capture, which means capture at the end of the frame that we're currently on. We have continuous capture. Maybe we want to do a time lapse. Does the surface change in time? We can select continuous capture, and the system will capture 1, capture 2, capture 3, capture 4 every time we finish scanning. We can do a capture now. Maybe the information that we need is already displayed on the screen. We don't need to wait for it to finish. We can press capture now, which will capture just this part of the information that we've already scanned. And if we don't want to capture, if we've enabled something and we want to stop that, we have this cancel capture or abort capture here. Okay. Now just to the right of those 4 icons, we have a text entry where we can choose what name we want to name this particular scan. So I'm going to call this just training here. And you see that we have now training. When I press enter, it will automatically put in some incremental number, because maybe I'm going to do a continuous capture and maybe that will be 100 frames. I don't want it overriding itself. So it will automatically increment that, and then the file name nomenclature, the file type, is called .spm. So this is what we call an SPM, or an image file. So if we press capture now, at the end of the frame, when we capture the last line in this frame, it's going to save that data, and you see a new patch here, a new icon has turned up here called training.0_0000.spm. So this is the image that I just captured. Now we want to see this image, maybe do some manipulation, maybe export the data. So if I double click from within this window here, what we open up in the background then is our Nanoscope analysis software. So now we have 2 software packages. We have the Nanoscope control software, Nanoscope 10.0 in this generation, and we have the Nanoscope analysis software, which is Nanoscope 3. So what we've brought up now is the Nanoscope analysis software by opening that file that we just saved directly out of the Nanoscope controlling software. So within the Nanoscope analysis software, we have some basic functions such as data manipulation, like flattening of the imaging, or exporting of the data, or taking cross sections and slices, rendering it in 2 dimensions or 3 dimensions. And so we have those in command format from the drop-down window here under analyses that we can do, or we have them as icons also across the top bar here. So for this particular image, why don't we go ahead and we will do a plane fit to it. Just do a second order plane fit. So we change the bow or the flatness of the sample. And let's have a look at how it looks in 3 dimensions. Here we can render it in 3 dimensions. And let's just make that for the cases of what we want to display. We'll just make that a little bit smaller here. So what we can see now is we can see our 3-dimensional view. This is the surface topography that we have. Now the AFM system here can capture more than just the surface topography, for example, roughness. It can also capture other information. And if I go across to this other file that I've already opened here, then we can start to look at other things. So there is a mode of operation here, a nanomechanical mapping mode called peak force quantitative nanomechanical mapping. And with that, we can start to see other things such as modulus, for example here, adhesion or chemical specificity on the surface, the deformability of the surface here, and the energy dissipation of the probe against the surface. So rather than just having surface topography or height, we can start to look at other properties of the surface to help determine a little bit more about what it is. And I can then overlay those mechanical properties or those associated properties over on this three-dimensional image that I've created here as well. So on this side here, I have something called plot type, which is mixed. So not just topography, I want something else. So let's say I want topography and I want to put adhesion. Adhesion is channel 5. So if I count it down, height is channel 1, in this case peak force error 2, DMT modulus 3, log of the DMT modulus 4, adhesion is 5. So if I click on adhesion here, we're going to overlay that adhesion channel and render it over the top of our height channel. So now the color scheme that we see is now from the adhesion channel, but the three-dimensional view that we have is the topography. So this is also a very good way to visualize what we see here on the sample surface. Okay, so if we're back in 2 dimensions, the other things that we can do, which are very useful, we could do a straight surface roughness. So if we have a look here, I click the roughness icon here, and I can then have a result of the surface roughness. The first part here is image. So that's the entire image that we've captured, analyzed the surface roughness, and we see here the RA, the average surface roughness of this surface, is around 3.13 nanometers, which is very small, and that's the purpose of this instrument, is to measure down in this nanoscales. But I can also take a subset, because that roughness includes these larger dots. Maybe I just want the roughness of a small section. So I can choose a small section, click and drag, and then I have here just the roughness, which is not the whole image roughness, but now just the roughness of this small section. And so you see the background roughness RA is only 0.436 nanometers, which is just a little bit over 4 angstroms of the average surface roughness, which is very tiny. Now maybe what I want to do is I want to actually measure some height or a cross section. I have a tool here called a section tool. So I can take that section tool and I can just click and drag and draw a line through a feature here, and that will give me the cross-sectional profile of that line. So if I want to measure height, I can take one cursor, drag it to a background level. I can have my other cursor here on a top level, and then I have these automated statistics down the bottom which can give me information such as the vertical distance, in this case for height. So the vertical distance from this point to this point, according to the measurement we've just made, is just a little bit over 24 nanometers. Now I could maybe want to measure the width of this object. So I could bring my cursors and I could put it, let's say, at this interface here. Let's say this interface here. And then I have a horizontal distance here, which is now 1.125 microns, okay? And so I don't just have to do one, I can do multiple if I want to. I can put in a second set of cursors, now you see coming in the red. So I could make a number of measurements across this surface if I want to. Now we won't go into it in this training, but there are other automated statistics that we can do, such as particle size analysis, which would then go along and analyze each of the size, height, and diameter distribution of all of these spots on the surface. So that's a slightly more advanced way of dealing with the surface. So you can see here the easy way to just display the data. In this case, we're making some very basic measurements, and we can capture this data. In this section of the training, what we're going to do is we're going to start to talk about a imaging mode, which is called peak force quantitative nanomechanical mapping, or peak force QNM. And the purpose of this mode, similar to what we're talking about before with topography, getting high resolution surface imaging, we're going to get high resolution now nanomechanical properties of the surface. So that's the stiffness or modulus of the surface, the adhesion between the tip and the sample surface. But in order to make this really quantitative, as the name suggests, we need to do a couple of basic operations in order to calibrate the system in order to get the best level of accuracy. So what we first start with for peak force QNM, this is a mode of operation. So within the Bruker's nanoscope software, if I want peak force QNM, we get presented with this experiment screen. This is mechanical properties, so quantitative mechanical property mapping. And I choose an experiment, which is quantitative nanomechanical mapping, and we're doing this in air. So peak force QNM in air. So this is the workspace that we're going to be working in. Now within this workspace, it is a little bit different, but only subtly so, but a little bit different from the previous workspace that we had. So let me just go through and briefly explain that. So within this current workspace that we're working in, you now have in the setup window, which we started out with, you now have another step in the setup here called probe calibration that we didn't have before. Okay. Within our window, within our scanning window, we now have a number of channels here which are now enabled by this mode peak force QNM. And so these are additional to the height and the peak force error that we had in the previous scanning of the topography. We now have DMT modulus, log of DMT modulus. We have adhesion, deformation, and dissipation as additional channels within this scanning window screen. So the first step that we have for peak force QNM calibration is to calibrate the cantilever. Now remember, the cantilever is part of the probe of the system, and it's in the setup window. So what we should always do to begin with is we should choose the probe that we're using. Now we're still using the Scan Assist Air probe that we had before. So I'm going to choose Scan Assist Air probe here, return and save changes. So that loads, like we said before, all of the defaults for this probe into the back of the system. So it's a nice starting point for the system, but it's not accurate enough to be really quantitative. So what we want to do is we want to then go into this advanced probe calibration mode, and we'll do then the full calibration of the probe. So what I've loaded into here is I've loaded in a sapphire sample, and if we have a look, you have two boxes which are called Peak Force QNM Sample Kit. And so these contain a number of samples in here which have different material properties, and they're there as a guide for us to use for this mode of operation, Peak Force QNM. But the first part of the calibration is to press the probe into something that we know is very hard, which won't be deformed by the cantilever. That's a very important point. So I've loaded up Sapphire. Sapphire has a very high modulus. It's in the 400, 450 gigapascals. So much stiffer than the probe that I'm currently using. And the reason that we want to choose a particular probe over one probe versus another probe is because the probe stiffness itself, combined with the property of the sample, can determine how well this technique works. So what we have in the help file is we have a nice simple table which looks at the type of stiffness that your sample will have. It looks at the type of probe that we may recommend for that sample stiffness and the nominal spring force constant of the cantilever of that particular type of probe. So if you use the Bruker probes, you've got a nice recommended list here. If you have some other specialty probes that you want to use, then you can gauge roughly what you might need according to your sample and according to the nominal spring force constant of the cantilever. So just be aware of this. It's in experimental guide, imaging modes, nanomechanical mapping, peak force QNM, peak force QNM probe selection, or alternately you can use the search function here. Just type in QNM and you'll see it's the first option, peak force QNM probe selection, bringing you to this. So we have Scan Assist Air Probe. This is good for soft materials in a few hundreds of megapascals, which is what we're going to image next. And we've set up this particular probe. You see here, probe type, Scan Assist Air. We've placed the crosshair, number 2. And now we're going to do the probe calibration, here, number 3. I'm going to click on this advanced button. Now, the first part of this probe calibration procedure is to measure the properties of the cantilever just hanging in space. The air that's around us in the room might be 20, 25 degrees, but that's far away from absolute zero temperature. And so that energy that we have at that temperature is going to cause this small beam that we have to oscillate. And so we can measure the characteristics of this cantilever beam oscillating in this room environment by doing what's called a thermal tune. So if I click on this first step here, it says Start Thermal Tune. I shall click on this one, and I'm just going to use this first option here, Calibrated Spring Force Constant, and it automatically puts in there 0.4 newtons per meter. Now this is not a calibrated number. This number is just the number that we get off the back of this Scan Assist Air probe box from the probe database. But we will calibrate this number later. Now, the thermal tune, the deflection sensitivity, which is a parameter that we're going to measure, and the cantilever stiffness, these two parameters are tied together. And so we need to actually know both in order to have a calibrated value. So what the system does when I press thermal tune is it sweeps the lock-in amplifier. We detect the laser reflecting onto the photo detector, and we can take that signal and we can pass it through a lock-in amplifier, and that can then give us a spectrum of the amplitude of the oscillation of the cantilever, how much it's vibrating as a function of the frequency of vibration. And so what we see here when we've completed is we have one main vibrational mode here, which is already automatically highlighted within these cursors. We have secondary and tertiary modes, which we can also see as well. The one that we want to use is this primary mode. Now, because we've loaded this probe already in the probe setup, the system knows where to look for this peak. It's a parameter in the system. For this particular cantilever, it's around about 70 kilohertz. It automatically calculates a nominal deflection sensitivity parameter. So all I need to do here, if this fit, which is red, matches the peak of the blue data, which is underneath here, then I know that the fit is good. So I can just click yes. And down the bottom here, return and save changes. So we store that thermal tune information and the values that we've just measured. That gets stored into the background and we use it in another step. So now what we do is we're going to engage with the sample surface. Similar to what we do with imaging, it's exactly the same. We're going to start the peak force tapping oscillation, and then we're going to start to move the probe closer and closer and closer to the surface until we finally touch the surface and we can detect that touch. In the meantime, what I'll do is explain deflection sensitivity. So as I take my cantilever, my laser is shining down on here. The cantilever beam is at some angle and it's reflecting off to my detector. So that path, if I press this cantilever down, I move some displacement, some distance, which I can measure in nanometers. That will cause my position to change by some voltage signal on the detector, which I can measure. Because remember, it's a quadrant cell photodetector. It's a position sensitive detector. And so that parameter that I want for deflection sensitivity is nanometers per volt. So when I push into a very hard surface, how much displacement have I pushed for the amount of signal that I generate? And this is done through a ramp. So you see we've done the first step, thermal tune, which we've saved in the background. We're now engaged with the sample surface. The third step here is to do the deflection sensitivity. Now, if I don't want to have to think about anything, I can just click ramp. The system will now press that probe into the surface 5 times. Okay? Each time we press into the surface, we are out of contact for a long way. We then press into the surface and we withdraw off the surface again. So you can imagine we are just pressing in, pulling away, pressing in, pulling away, 5 times, just to give us a nice average. And so we now measure the slope of this red part of the curve here. That slope, because this surface is very, very stiff compared to the springiness of my cantilever beam, then we can measure this, and we know that the measurement of deflection sensitivity is entirely the function of the probe as it pushes against the surface, just bending out of the way under that applied displacement. So this value that we have now, deflection sensitivity here, is a parameter that is now calibrated by these ramps that we've done against the surface. So you see the previous values that we estimated from the thermal tune, we had a deflection sensitivity of 31.6 nanometers per volt and a spring force constant of 0.4 newtons per meter. Now we've actually measured the thermal tune and we've measured the deflection sensitivity accurately. We now have a calibrated deflection sensitivity of 32.2 for this particular probe and a calibrated spring force constant of 0.38 for this particular probe. So very close to the nominal values that we had. Okay? The next step that we need to do is to now calibrate the deflection of the cantilever, not in a linear static move towards the surface and pull away, but now in a dynamic sinusoidal environment where the probe may be oscillating up and down like this under some motion, where we're pushing the probe back and forth now sinusoidally. So we can choose then the frequency that we want to use. So in this case, the default is 4 kilohertz, 2 kilohertz, 1 kilohertz, 0.5 and 0.25. The value that we should choose here should be dependent on the imaging that we've already done. So if we've taken our sample, we've imaged it with this probe, we go, this is a good frequency that this probe works for imaging this sample. I'm then going to choose that frequency here. So let's choose, for example, 2 kilohertz. The system will switch to a 2 kilohertz drive and I can simply click calibrate. The system then captures this curve here. It looks very similar to the ramp that we did before. The ramp is linear drive in towards the surface. This ramp here that we've done is sinusoidal. We're just bouncing up and down off the surface, in this case at 2 kilohertz. But importantly for us, we generate a value called the sync distance QNM and the peak force amplitude sensitivity. So these two parameters tie the response of the signal here back to this deflection that we've done. The deflection that we've done here now ties us back to classical mechanics, which allows us to make measurements of modulus. If I wanted to do, let's say I didn't know the frequency that was best for imaging my surface, I can actually come in, sorry, before I do that, we now need to press update and verify current values. So it makes the measurement a second time and we take that second measurement and we can see it's very similar to the initial measurement that we've done. Okay? Now if I want to do a different frequency, maybe 2 kilohertz isn't good, or maybe I don't know what frequency works best, I can go ahead and calibrate all of the frequencies here or just a selection that I think will be useful. So I've changed over now to 4 kilohertz. I'm going to click calibrate. I'm going to press update and verify current values. And we'll do 1 kilohertz as well, where I choose 1 kilohertz here. I'm going to press calibrate and I'm going to press update and verify current calibration. And again, what I'm looking for here is that when I press update and verify, I'm looking at my new values that I just generated are very similar to the ones that I did just a few seconds ago, which they should be. So now what I have is I have my cantilever beam is calibrated in this system in the room for today, in the environment that we have, in the temperature that we have. So I'll go ahead and press return and save updated values. So now what we have is we have the cantilever beam is calibrated for measurement of mechanical property. The next step that we're going to do now, we know that we're calibrated against this surface, but what we want to do is we actually want to have our sample in there. So I'm going to withdraw away from the surface. Every time I click withdraw button here, I pull away from the surface around about 30 to 50 micron. So I'm going to press that a couple of times. We're going to change the sample right now. So I've pressed that a couple of times. I'm going to come across to my instrument and I'm going to move the tip away from the surface. So moving the tip away from the surface, I'm moving the tip up. So you see here a label tip up. So I'm going to bring that in, move the tip up. And now what I'll do is I will reach around the back here to my securing knob, which secures the probe holder in place and loose it like we showed you before. I'm going to take this probe holder out. And this probe holder I'm just going to rest, for example, on its edge, somewhere where I'm not going to knock it. I'll give you an example. We'll just put it here. I'm going to take my sample box, which is the one that I'm using, this one here. Just bring it somewhere convenient, and I'm going to take this sample out. So I find the easiest way to do that is just to drag it off the magnetic base, and then we'll grab it and lift it out of the system. That's very easy. All right, the sample that I'm going to put in is a sample that's called PSLDPE, or polystyrene low density polyethylene. And the part that we're interested in this case is the low density polyethylene. So I'm going to just drop that in, and I'm going to put that nicely in the center here. Now, as we mentioned before, you can be aware of the sample height. You're changing samples, the thickness of that sample matters. Now, I know for this case, in this particular case, the sapphire sample is slightly thicker than this low density polyethylene sample, so it's safe for me to put this probe holder back in straight away. But it may not be the case for your sample. So just remember when you're changing samples to be conscious of the height of the sample relative to the 3 balls that are inside the system like we showed you before. So I'm going to go ahead and place this probe holder back in. Now it rests on those 4 balls, so it's a kinematic mount. So I don't want to change anymore, adjust any laser or any other parameters in the system. It's not necessary. Okay? So what I want to do now is I want to come back across to my software here, and I want to look to my video screen. Let's just undock that so we can see it. And I'm going to focus again now back to the sample surface. I'm going to bring the probe close to the sample surface so we don't have to waste a lot of time landing on the surface. So let's go ahead here and adjust our knob. Bring our tip into focus. If I go down, I see some sample contrast here. So I'm focused on the sample surface right around there. Okay. Now what I want to do is I want to just raise this up a fraction. So it's just out of focus a little bit. And then I'm going to bring my probe into focus. This way, when we bring our AFM probe down, we're not going to be touching the surface of the sample. So I have a little bit of offset in the focus of the optics. Okay. So we see now that the probe is getting close. We see that the probe is starting to come into focus, but there's still a gap between the probe and the sample surface, albeit very small. Okay. So let's redock this. So just to recap, we've been in the setup menu. We've already aligned the probe and the laser system, and we've done the calibration of this probe. And what we're calibrating is we're calibrating the properties of the cantilever in order to give us a way to measure mechanical property of a surface. So we're done with the setup. Let's go into check parameters. We're going to leave here for the moment everything as default. I'm just going to change this again back to 2 kilohertz. I recommend for this mode with this particular instrument to run at 2 kilohertz for mechanical properties, or 1 kilohertz if you're using a standard sort of stiff polymers out even into maybe some softer metals, something like that, the 1 to 2 kilohertz is best. 4 kilohertz, the measurement won't be quite as accurate, so we prefer to use at 2 kilohertz for this particular instrument. Okay, so let's engage. Again, we'll land on the sample surface. We start the peak force cycle, which you will hear as a kind of a high pitch in the background. We land against the sample surface, and we know we're touching because, again, we can see the interaction of the probe against the surface. Now, Scan Assist is turned on, so it automatically adjusts the parameters in order to give us an image eventually, which we will get here, like this. So we start to see some imaging of the surface. Now we're going to hunt around and let's just have a look for a feature that we're interested in. Now I'm just going to type in 5U. So the prefix or the suffix here, 5U, U stands for micron. I could put in N for nanometer. Just gives us a quick way. I don't have to type out 5,000 nanometers. I can just type in 5 microns. All right. So now what I see, if I rescale here, the data set, I now see a surface which starts to have some features appearing. Now this particular surface is a film of polystyrene, which is around about 2.5 to 3 gigapascals. For this particular AFM probe, we won't be able to measure that very accurately. What we're interested in is this low density polyethylene, which is usually around 100 to 300 megapascals, so around 10 times less. And this probe will measure the modulus and mechanical properties of this surface very well. So what we see now is this is the region that we're interested in. So I'm going to go ahead and click this zoom. And I'm just going to zoom around one of these here and click execute. So what we're starting to see now is we're seeing then the topography that's associated with this region of the surface. And you see when I clicked in zoom, I've changed now my scale. It's no longer 5 microns. It's now 1.66. And you see it's also changed the XY offset as well, according to the position that I've chosen. So the windows that I have that are automatically opened right now is the height window, so surface topography, what does the surface look like? There is the peak force error, which is the signal that we use to generate this height signal with the system in feedback. We then have a modulus channel or mechanical property of the sample surface, such as stiffness modulus, and I have the log of that channel as well. But I can also choose to see the other channels such as adhesion, deformation, and dissipation. So if I wanted to bring one of those channels into this window, all I need to do is click the window where I want it to go. So I'm going to overlay this peak force error window with something more interesting. And I'm going to choose it here first, so you see it's highlighted in blue. And then I'm going to click the channel that I want to be there, in this case adhesion, here. You see it automatically changes. Okay, and now what we see now is that we can see pretty clearly two interesting things for this particular sample. So we see in the adhesion channel here that we have this very strong contrast between the film and this surface here. You see a big jump in the adhesion. So this is due to the fact that this probe binds differently to the surface of the polystyrene molecules than it does to the low density polyethylene. We see that the polystyrene film, which we know is this outer film, is stiffer than the low density polyethylene film, which you see here is this dark patch in the middle. But the low density polyethylene film is the film that we actually want. Now the software is rescaling everything in order to get all the data on the screen at once, but that may be not useful to us. What we're going to do here is we're going to adjust this. Now this is a real-time adjustment of this window. It doesn't translate to changing the data that we save. It's just for us to visualize. So I'm going to change the center position, and I'm going to make the center in this case to be 0. So 0 gigapascals, and I'm going to change the scale. The scale is the amount of data around that center position that we're going to render to this window. So I'm going to change this one here to maybe, let's see if it's 1 gigapascal, maybe 0.7. Okay. Let's just change this offset a little bit to be maybe 0.2. Okay. So what we can see now, I've changed the center position to be around 50 megapascals and the data range that we rendered to be 200 megapascals. And so what we can see is we can start to see that there is actually some mechanical structure. We can see it here in the modulus channel. We can see it here in the adhesion channel. And we can also see a little bit here in the topography. So the advantage of this technique is that we can now break out down to the nanoscale, really in the nano regime, mechanical property differentiation between each of these data channels. Now there is one further calibration which we won't go into within this training session, which is then calibrating the shape and the radius of probe, of the apex of the probe. And we'll cover that in a different training session. So for now what you have is you have a probe which is calibrated for the cantilever stiffness, which can separate out topography and mechanical properties such as adhesion and modulus, and let's say here deformation or how compressible the material is. So you have this data that's available to you, and it can be rendered really down to the nanoscale. So what we want to talk about now is we're just going to talk a little bit about operator safety and things to do and things definitely not to do, or things to avoid within this instrument when you're setting it up in order to make it safe for you as an operator and safe for the instrument as well. So the first and most obvious thing with any electronic component is we don't want to be removing any electrical connection in the system while the system is powered on. So these would be things like the connections on the side here, or around the back of the instrument, as you'll see, will be some electrical plugs for the AFM head and for the scanner. We don't want to remove any cables while the system is powered up. Obviously, we don't want to come here and push the system around. We should be delicate. This is an instrument that can measure down to angstrom level surfaces and very precise. So we don't want to manhandle or roughly handle this system, I should say, in any way. And so the other things then when we come to operate the system, you'll be using samples that you create, which will be either on magnetic metal puck, and they'll have different thicknesses and sizes. So within this instrument, what we recommend is that your sample diameter be not more than around 15 millimeters, and the thickness overall, including that magnetic metal puck, be no more than 6 millimeters high. So within the head, which we've seen in another section, is we have a probe holder here, and then a sample which is magnetically mounted to the piezo scanner. And so the piezo scanner out of the entire instrument is the most delicate part of the instrument. Now that's the part which is moving the sample back and forth at this angstrom scale. So we need to be careful not to shock or knock that in any way. So in order to take samples in and out of the system, we're going to take some tweezers. So we're going to take some tweezers, and we'll typically slide the sample out to the side. Now remember, this is magnetic, so we're going to try and grab it here and lift it off. So now I have here my sample which I've put in, and I'm going to use a different sample, but you see that all of the samples here, they may have different thicknesses, varying thickness, different substrate, different type of material. So when I swap from one sample here, 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 to different ones, I need to be mindful that when I put this other sample in, and I put my AFM probe holder in with my cantilever beam, with my cantilever on it, I don't just automatically crush that against the surface. So you will remember from the earlier setup part of the video that we have tip up and tip down, moving this entire head section here up and down against reference to the sample surface. So what I like to do in order to make sure that my sample is not going to get, or tip is not going to get crushed by my sample, is I'll get down nice and low here and I'll actually look across the surface. So let me mount in a thick sample. In this case here, the thickest one that I have within this sample kit is HOPG. It's just a little bit over 1.5 millimeters thick in the sample plus the metal disc as well. So it's about twice the thickness of the sample that we just had on. So what we've done is we put the HOPG sample in, and now we want to make it safe. I don't want to put this in and crush my AFM probe. So what I like to do is I like to look down low and look across the sample surface, and I look to see where the top of that sample surface is relative to these kinematic indexing balls here. Now you'll remember in this system that when I move up and down, I move everything relative to what I define to be the tip position. So in order to move this sample out of the way of the tip, then I need to move the tip up. So I'm going to come over to my motorized switch on the right hand side of the instrument, and I'm going to go tip up. Now what I'm looking for when I'm looking across the top surface of the sample, I'm looking for that to be a little bit lower than the top of the ball part of those balls, so the top of the curve of those balls. So right now we're moving this head. When I say tip up, this head is lifting up. So it's going to increase the separation between my tip and my sample. So I'm going to continue to come up now. The top surface of the HOPG is now level with the top of the balls, and I'm going to continue to come up until it's a little bit below. Okay. So what you see now is you see the top surface of that sample. It's now sitting below the curvature of the ball. So I know in this case that when I put this probe holder in, I'm not going to just straight away crush the tip of this cantilever that I've just installed against the surface. So let me just slide that in. Now when I slide this in, we're going to slide it in from an angle coming in from the top. What I don't want to do is take the back edge of this here and just push it straight across, because maybe I'd rub against the top surface of my sample and damage it. So I'm going to slide this in here and I'm going to place it down. Now because we have kinematic balls in this system, it's going to come down into one resting position. There we are. So now I can feel with my hand that that is kind of nestled onto those three balls, and I'm going to take the back lever and I'm going to bring that lever down just to put a little bit of pressure on it. I don't have to use a lot of pressure to tighten it right down, because I don't want to break that lever arm. I just need enough pressure on it just to secure it in place and to keep it stable. Okay, so something like this. So now from this point here we can carry on with the setup of the system. But again, keeping in mind here, the most delicate part of the system is the scanner, which is this part here, and what we mount the sample on is the end of the scanner. What I don't want to do is then push that scanner in any way or knock it or shock it, okay? So once you're done with your experiment, you've finished your scans, you've taken your sample out, and you've secured it away, what we would recommend you do is load the probe, take the probe holder out and take the probe out as we've showed you before and put it away in its case so it's secure for the next user or the next time you come back to use it. And then what we want to do is just shut the system down. So normally the general shutdown at the end of the day will be very straightforward. Turn off the software, turn here, power down the nanoscope control, the nanoscope analysis software when we're done. You can shut the PC down then. So just the standard way we shut down the PC, power down, shut down here, and turn the fiber light off down here. You can leave the nanoscope controller running. We would normally only turn the nanoscope controller off when we are finished for a long segment, or maybe there will be a holiday or a long weekend, or if we know there will be a power shutdown, you can leave it on. Otherwise, it should be fine. If you do need to turn it off, the power switch for this particular controller is on the back side of the instrument. So the instrument at the front we see here, but in the back corner we have the power switch. But you shouldn't have to, under normal operation, worry about turning this off. Okay, so now what we have is we've got our instrument set up, our sample is loaded in here, we're good to go. If we want the best environment possible for our sample, particularly if we're looking at very small, very smooth surfaces, we want to try and get the best out of this instrument, we want to close this acoustic enclosure down. So what we do is we're going to lift this out and push it down, and then as we come to the bottom here, we're just going to push on this door a bit and secure it with this lock. So turning that one there clockwise, and that will latch this down. So you see this is now nice and secure in place. Obviously, when we are finished doing what we need to do, we want to get our sample out. We're going to turn it the opposite way here, and it's quite stiff because we want a really good acoustic seal. And we're going to turn that all the way until it stops. That will disengage the lever, lift it out slightly, and then let it come up. The acoustic enclosure door here has two high pressure struts on the back to help us lift it up and out of the way. All right, so now what we've done here is we've taken apart the system that was in the enclosure. Now, under normal circumstance, you're not going to be doing this. We're doing this just to explain each of the parts. So if you have a look at what we have on the bench here, we have the AFM base, this part here. Now this AFM base, in the bottom of it we have a motor. We have various electronics in here for the interfacing. If you have a look on this side, this is where our ribbon cable was plugged in. Okay, and now on the front, our LCD screen, and you see on this side here, this is the mode selection switch. So this side here determines what gets displayed on this screen. Now normally we have this set to AFM and LFM, but it is possible for another mode called tapping mode to be in TM AFM. Again, it's only changing what's displayed here, nothing more. On this other side, if I turn this around here, you see you have another switch here, which has a label tip up and tip down, which we've put on. So this is the one where we're talking about moving the probe towards the surface, tip down, or away from the surface, tip up. So if I want to move the probe away, all we do is we go tip up, and I simply switch this down. Now this is a momentary switch, so when I let go of it, it automatically comes back to the off position. Same if I go tip down, I move down, then I let go, back to the center position, okay? Now, you'll see a flexible coupling just in here in the middle. So this is taking the rotation of the motor, which is in the base, passing it up through this flexible bellows into what you see here is a little coupling. Now that coupling goes to the bottom of the scanner. Now out of the entire system, this is probably the most delicate component of the system. So this is the piezo scanner. So inside this mount we have the motor passing up into this lead screw. This pushes this entire assembly up and down relative to this center component here. Now this center component that we see, which has this beige white cap on it, that's actually the piezo scanner. So this is a piezo ceramic. It's very thin walled, and it allows us to move in a very precise motion down at the nano and angstrom scale and over a range of around 10 to 15 microns for this particular scanner. So this particular scanner is called the E-scanner, which is a high resolution, nominally 10 micron, but this one will do around 12 microns. And you can see it's designated an E on the front. So this one here, it slots into here, like that. And then we'll have a locking screw which comes up underneath. But remember, you're not getting down to the level of disassembling this. So on top of this piezo scanner, what I want to show you here is that we have three balls. One here, there's one at the back, here, and there's another one around this side here. So those three balls are kinematic indexing positions, which made up with the bottom of the AFM head, which is here. So on the underneath side here, you see also a slot, a ball, and then a blank. So in that configuration, when I place this over the top, it will always go back to the same position. Now, placing this on and off the system, again, it's not something that you would normally be doing, but it's something that we're doing here just to show you and demonstrate and explain the components. Because this is the most delicate part of the system, when I'm raising and lowering this off the surface, off this mount here, I am making sure that none of this actually hits into here, okay? So what I would normally do, I'm just going to spin this around a little bit so that I can see it from my side. Just going to gently place that down over the top. Now this holds down onto the surface. There we are. So this is holding down onto the surface via these springs that are on the side, and there is a little beam underneath. And I'll take this off because we want to explain what this head is. But whenever I take these springs on and off, I need to make sure that I hold the head securely to stop it from pulling off like that, okay? So whenever I have those springs on, I'm holding the head down in order to put those springs, and then that holds on nice and secure on the top, okay? If I have a look around the back side here, I have then an electrical cable coming from the head, which gets plugged into this side here. Yep, in that orientation. This is a D connector, so you can't plug it in backwards, but the pins are very fine, so you don't want to crush them. And then I have a cable for my scanner here, which is the smaller one. So it's even a different size, so we can't mix them up. They only go one place each, okay? So always check that these are in and they're pushed and seated into position. Okay. What we're going to do now is just talk a little bit about the layout of the AFM head. So I'm just going to take it off the system. So I'm going to take those cables out. Okay. Let's take the spring off one side while holding it in position. Spring off the other side. And then I'm going to gently lift this straight up, not left and right at all. Okay. So this is the AFM head. The purpose of this head is to take a laser beam, shine it down onto the back side of the cantilever surface, reflect it up to the detector. So let's talk about that process. On the top of the head, our laser is coming from this corner here. It's going to shine along, and then if you have a look inside here, you see a very tiny prism. That tiny prism is going to take the laser beam and reflect it straight down through the system. It's going to catch the side of the cantilever. It's going to reflect off that cantilever, and then if you have a look on the inside here, you'll see on this right-hand side there is a mirror. So the laser beam is going to hit that mirror and then go sideways into this side of the system where we have our detector module. Now, we also have inside here, if you have a look, there is a U-shaped clamp which I can control from the back side. So if I actuate that, you see the clamp is coming down there. If I do it the other way, the clamp is coming up. Now, there is also a tilt for this mirror as well. So let's turn this around. On the back side of the system, I have one knob here in the center. This is the one for that U-shaped clamp. I rotate it to tighten it. I loosen it off to unloosen it. The mirror position, I generally don't have to touch. Only if I can't find the reflection of the laser in the detector, I may need to make a very fine adjustment on this lever arm here. So this lever arm changes the position of this mirror on the side. So let me go ahead and just move that around so you can see that. So you can see now the mirror tilting up and down a little bit. So this is only for bulk. We don't worry about it for anything else. And for more often than not, you won't have to worry about this lever, only for making big changes. Okay, now if we have a look around the back again, my laser position, to adjust the position of the laser to the back of the cantilever, I have two knobs that are on the top. So if you're facing the instrument from that way, these two knobs at the top here adjust the position of the laser relative to my AFM probe and the cantilever. Once the laser has caught my sum signal is very big, then I adjust the photodetector. So there are also two knobs on the photodetector, this one here in the vertical axis, and then on the back side we have one in line here, this one here, for the horizontal axis. Okay. Now this entire head can move around relative to the sample. So if I want to place the tip at a very particular position, then I also have two more knobs, one here on this side and then another knob down at the front. So when this is placed on the system, let me just bring this across here. So when this is placed on the system and it is secured down in place, if I adjust this knob and this knob, it adjusts the position of the tip across the sample so I can put the tip exactly where I want it on the sample surface. Okay. So inside of this head, we need to place a cantilever holder or a probe holder. So that is these objects here. Okay. So these probe holders, if you have a look inside the head here, you can see we have three balls. So those three balls are, in the same way as the scanner, they're mounting onto the back of this holder. So this holder I can take in and out, and it will always go back into the same position relative to this head. And so to do that, I have this little arm which I can grab. Obviously the bottom surface here with the bigger cutaway goes down, and I'm going to slide it in at an angle, making sure that my clamp is raised out of the way. So with the clamp raised out of the way, what I'm going to do is take this holder and I can slide it into the system at an angle and let it down. And now what you'll see is that that is actually sitting in an indexed position there. So if I pull it forward a little bit, it'll drop back into the same place. Just take it, unseat it a little bit and let go. It's dropping into the same place. So then once that's in, I'm tightening this knob on the back here. And what I'm going to do is I'm going to bring that down until the arms that you see coming down on the left and the right hand side there touch against the surface here. And we see a little bit of deflection. I can feel a little bit of resistance. I don't need much. I don't need to use all of my strength to tighten it down. It's not necessary. Just need enough to bring it down to touch. That just stabilizes the probe holder. Okay. So now what we'll do is we'll talk a little bit about exchanging probes. So the probe holder, if we flip it over, okay, our probe holder here has a gold clip which presses down onto the surface of one of our cantilever chips. So the big part that we can see is called a chip. Hanging out the end of that is a cantilever, and then underneath touching the surface is the tip. That's the nomenclature that we use. So in order to get this probe in and out, I'm going to take a sharp pair of tweezers, usually like these angled tweezers we find to be quite convenient, and I'm going to place this down on a flat surface like the table here. Now on the back surface, you see there is a little knob here. There is some electrical connections. This little knob that's here is actually a spring. So as I press down here, you'll see that that little gold leaf spring lifts up. So that releases the tension that's on the cantilever probe and we can take it in and out. Now in our box, our cantilevers are labelled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the standard way for Bruker is the AFM probe, the cantilever beam, on a new probe will be on the upper side. Okay? When we place a probe that we've used back into the box, we're going to place it at an angle. That way I can visually see at any time which is the new probe, which is a probe that may be used. Now if I've broken a probe the cantilever is gone, I'm not placing it back into this box because it's just going to waste your time looking and putting it in and getting it installed. You may waste 5 or 10 minutes. It's unnecessary. So we don't place it back in the box if it's broken. All right, so what I do is I try and have then my box ready to go. I'll have my cantilever probe holder here, and then I'm going to press down nice and secure. Now I'm right-handed, so I have my tweezers in my right hand, and I'm going to take this probe out by just sliding the tweezers very gently underneath the front end and grabbing the probe out. That's the way I find to be the easiest way to take it out. The other way is to grab it from the top and very gently lift it out from the very top. Personally, I find that way is a little bit harder. Okay. So what we're going to do now is we need to install the probe into this holder. Now, we have the spring here, but the probe sits in a recess underneath, and if I just use my tweezer here, that recess that's in here is actually stepped in. Okay. So what I'm going to do is I'm going to take my probe. I'm again right-handed. The cantilever is hanging out in space. So I'm going to take the probe towards the cantilever end, grab it gently with my tweezers like this, press down, and then slide it underneath that spring clip. Now it may take a little bit of practice to do, but it's not very hard. Once it's in, I want to gently press it down and just make sure it's slid all the way to the back surface where there's another step, and off to one side. Whether it is the front or the back, there's a little bit of play, but not much. Now as soon as I let go of my pressure, that spring is now holding that in place. So I can take that and shake it. I'm never going to get that probe out. So that is the easy way to put the probe into this cantilever holder. This probe holder will go into the AFM head, okay, when the system is assembled. Once again, I'll just stress that you're not going to break this down into this level of components. It's not necessary. The system will be assembled already in the system, but be aware that the two knobs on the top here, these two knobs are for the laser. If we have a look inside, the lever arm that goes up and down to secure my probe holder, that's controlled by this knob that's in the middle on the back side. The mirror position, angle, is controlled by this lever arm here. And then once I've caught the laser onto my cantilever beam, I need to adjust the photodetector. That's done by the two knobs, one at the top and the one on the very outer edge on the back side.